ring, which is our key-value store that allows users to change storage scheme of key-value pairs without compromising efficiency and consistency. The problem of storing data reliably is a well-established problem, and in response to a variety of application requirements, many storage schemes have been developed. The most popular one is replication, when the client sends its data to key-value store where it's replicated or like multiple copies are made. And like replication, in erasure codes, no additional copies made, and key-value store generates special parity updates which are propagated to the parity nodes. So in this work we focus on read-Solomon codes, and you're probably familiar with them from RAID 5 and RAID 6 storage systems. And finally, in-memory key-value store can be used as a caching layer, for example, for caching query results where no redundancy is present. So different storage schemes, they have different advantages and disadvantages. Replication is a simple scheme which provides a decent level of reliability and availability. However, it has really high storage overhead. On the other hand, read-Solomon codes, they provide the lowest possible storage overhead, but it involves computation to generate, update, and recover data. And finally, caching is the fastest way to store your data since there is no redundancy. However, it's not fault tolerant. And what is more, different storage schemes, they provide different trade-offs in utilization, in reliability, availability, performance, and utilization of cluster resources such as memory, memory usage, network load, and CPU load. Here you can see comparison between caching, where is no redundancy, replication-free when we have overall free data copies, and read-Solomon free too, when we have free data nodes and 2 parity nodes. The problem of, or weakness of existing key-value stores that they support only one such storage scheme, and as a result, companies maintain dozens of distinct key-value stores which has to be maintained separately, and they could even have different APIs. And it increases complexity of deployment of the system. So, and also it's not even clear how you can move the objects across the key-value store and be atomic. So clearly there is a need in a key-value store which can support multiple storage schemes, but now I'd like to introduce use cases of such key-value store. First of all, the potence of the data can change over time by intrinsic nature of the data. So we have, for example, we can have temporal computations, and they shouldn't be stored redundantly. And when we've finished our computation, then we would like to store them durably. Then we could make additional copies, for example. Or, for example, in Snapchat, when you upload your picture, they have to be stored reliably only during the first day of your, after the first day once you upload your data. And then the redundancy or the reliability requirements of your data can decrease since your picture will vanish anyway soon. So I'd also like to point out requirements the key-value store has to comply with in order to enable such use case. First of all, user has to be able to change storage scheme at key granularity, and also user shouldn't know how data is stored in order to access it, so it has to know only the key of the object. The second use case is multi-temperature data management. Quite often in data stores we can distinguish between hot and cool data depending on the access frequency. So cool data is less frequently accessed, and to optimize utilization of cluster resources, it's usually stored with read-Solomon scheme. So to enable this use case, we need to support both replication and erasure coding, and plus the changes of the storage scheme, they have to be immediately visible to all other clients. Finally, there have been many work on relaxing consistency to tune performance. Here we proposing tune performance through changing storage schemes. And to enable this case, the process of changing storage scheme has to be cheap, and it has to be consistent. So our key-value store complies with all these requirements, and it supports the following API. Here we have conventional function like get, put, and delete. When the client is oblivious to how data is stored, or he can client can specify how he wants to store the data with specifying the ID of the storage schemes. And with create call, client can assign a storage scheme to create storage scheme and assign it to some ID. For example, client can create replication 3 and assign it to ID 0, and then use this ID when he writes data to the key value store. And also he can change on the fly the current storage scheme with a move request when he can specify only the key of the object and the desired storage scheme. So I can talk a lot about all challenges. Now I'd like to focus on the solution. The key to achieving high performance is to reduce communication overhead. So we chose decentralized architecture where we have assigned key shards to the physical nodes, and the client applies a hash function to the key and then direct its request to the required machine. And the key idea here is that we stack together different storage schemes which share the same key to node mapping. So here we call this storage scheme memjust, and in this example they all have the same number of key shards which is equal to 3, or they actually have the same key mapping. So since on every physical machine we have all storage scheme, this request can be directed locally further to the required or requested storage scheme. The problem here that not all storage scheme can have the same number of key shards. And the problem comes from read-Solomon scheme. In read-Solomon scheme, the number of key shards or number of data node is actually strictly connected to the encoding. So to circumvent this limitation, we designed our modification to read-Solomon, which we called stretch read-Solomon, and I'd like to introduce it on the next slide. So here we can see read-Solomon to 1. We have 2 data nodes, one parity node, and the data on the parity node is equal to XORing data on the node 1 and node 2. So in other words, D1 plus D2 is equal to P1. And here we have 2 data nodes, the 2 primary nodes which can be accessed, so we have only 2 key shards. And if we'd like to have 3 key shards, as in the previous example, we need to do something. And what we are proposing, first, we need to split our data. It doesn't change, encoding can just change the granularity of the updates or granularity of coding, but the data stored will be exactly the same. And then we actually distribute these blocks over as many machines as we want. In this case, it's 3. So every machine will get 2 blocks instead of 3. And the key idea here is to preserve the coding scheme. By preserving coding scheme, we inherit all properties of original read-Solomon. So stretch modification will have exactly the same properties as the original one, and the only concern is reliability. Since we increase the number of machines, and then in this case, since we increase the number of machines, the probability of single failure has to increase. And we'd like to study how it influences reliability. So we performed reliability analysis based on continuous time Markov chain model, and here you can see reliability of read-Solomon to 1. It has reliability a little bit less than 4 nines, and it has 2 shards. And we right now can stretch it over 3 machines, 4, 5, 6, 7. As we can see, the reliability didn't change much, and sometimes it goes down or goes up, but it actually stays the same. We performed the same analysis for different read-Solomon schemes, and we showed that in all cases we studied, the reliability hasn't been changed dramatically. And also you can see a small artifact here, for example, read-Solomon 3.2. When we stretch it over 6 machines, it even increases reliability, and we describe this artifact in the paper, so have a look. Now I'd like to have a closer look at the architecture. Here we have 5 machines where the 3 machines, their primary one, we assign 3 shards to them, and the 2 machines at the bottom, we call them redundant one. They use just for storing replicas or partitions. So when users ask to add read-Solomon to 1, we said we have 3 key shards and we have to use stretch modification. So we add stretch read-Solomon to 1.3. Then the user could ask to add read-Solomon 3.2, we can easily add it, or then user can ask to add storage scheme with no redundancy, we call it replication 1, since there is only one copy of the data, and number 3 stays for the number of shards. When the client asks to add replication scheme, we partition the replication scheme into 3 shards and make replicas for each shard. And the same way we can do for replication 5. So the key idea here that all the storage schemes, they have the same key to node mapping, and the key will be assigned to unique physical node. So on the physical node, we have multiple different storage primaries of all storage schemes, and in this case, there will be only one coordinator of this particular key, and we can easily change the storage scheme. So if we'd like to change this, and we resolve problem with consistency by using versioning. Basically, when we change the data or move update the storage scheme, we just increment the version, and the client will always access the latest version of the key. So now I'd like to move to evaluations. We done all our tests on our 12-node InfiniBand cluster. Current implementation use RDMA, and it's single-threaded. For array codes, we used Zero Sure library, quite famous open source library, and all tests we did with 7 different storage schemes, which we call MapJest, and with 3 key shards. Here I'd like to focus on the main result. Other evaluation you can find in the paper. Here you can see the put latency for 4 different MapJests. When replication 1, it's no redundancy, replication 2, replication 4, and straight read Solomon 3.2. So as we can see that all these schemes, as we said, they have completely different trade-offs in terms of latency, but now I'd like it compared to the move request which we introduced. As we remember, to move the data, we just need the key and specify the storage scheme. So on the right part of the slide, you can see the latency of the move request. As we can see, for the smaller sizes, we have additional overhead. It comes from the fact that we have to resolve versioning, but later the latency it's actually reduces. And the reason for this is that when the client sends move request, he doesn't send the data to the key value store because it's already had it. That's why it pays off more when you have larger objects. In the paper you could find more evaluation when we compare our key value store with other systems, but it's not the main idea of our key value store. We're not trying to compete in performance with our key value store. What we want to show that actually you could support multiple storage schemes at low cost and without compromising API or consistency or efficiency. So to conclude, we design. To our knowledge, this is the first key value store which allows user to change storage scheme on the fly at low cost. And for this, we had smart allocation of our storage scheme and the key shards. And for this, we designed a straight read Solomon scheme to have an arbitrary number of shards for read Solomon schemes. Thank you for your attention. Any questions?
Let's thank the speaker. So we have time for questions. So while you're all thinking about the question that you want to ask, let me start by asking about your API. So you have this key-centric API that gives you a lot of flexibility, but what about bulk updates? So if I want to, change my storage policy affecting all of my keys or a large group of my keys?
Unfortunately, we haven't implemented it. It's possible, but I think it would be difficult to enforce strong consistency. In that case, when you have multiple updates, then you need something like transactions. It would be more challenging.
So do you think in practice you would require efficient support for these kinds of bulk updates, or could you get away without having it and then not having to worry about a strong consistency?
I cannot think about application, but for example, Redis, it supports like bulk update, but you never have this fine granularity for each key. And I think for many applications, more important to have it per key rather than per the range of keys.
Okay. So any other questions?
Yeah. If you have other questions, we can discuss it also offline after the conference. I will be happy to discuss other details of the paper.
There's one question there.
Hello, really good talk. So I would like to ask what kind of strong consistency do you support? Is it per-key sequential consistency or linearizability, or how do you define it?
Linearizability.
Linearizability. So you invalidate all of the. So do you have a primary, or how do you guarantee such a thing?
Since we have one coordinator of the key,
Okay.
this node is responsible for everything.
Okay, thank you.
So any other questions? Okay, so let's thank the speaker again. Okay, so the next talk is going to be presented by Mainak Ghosh, who is finally a PhD student at the University of Illinois at Urbana-Champaign. He's going to join Twitter after graduating. And today he's going to talk about how to reduce memory costs for analytics engines.
Thanks, Peter, for the introduction. Today, we will talk about our system GetFX, which reduces memory in interactive analytics engine. Before diving into the solution, we will briefly describe the space and the motivation. The real-time analytics space can be divided into two verticals, streaming analytics and distributed OLAP. Systems like SAMZA, Heron fall into the streaming space, while Apache Kylene and SQL Server are some examples of OLAP systems. In the intersection lies interactive analytics engines. Some popular systems in this space are Druid, Presto. The area is expected to grow to $13.7 billion by 2021. I'll introduce the different modules in interactive analytics engine next. A typical use case is add-click pipeline. Batch add data and real-time add-click events are collected, batched by time, and stored in a deep storage like Amazon S3. The individual blocks are called segments, and they are immutable. Queries are executed in a front-end compute node, typically VMs from Amazon EC2. They have powerful processors and large amount of memory. To reduce query response time, data is prefetched and cached in this memory. Additionally, data can be replicated to handle extra load to queries from popular segments. Further, so a typical production deployment can handle petabytes of data and millions of queries per day. As a result, the front-end compute nodes may require a large amount of memory. Note, in this talk, we focus on replication, as reducing replication can lead to reduction in memory. We are interested in reducing memory because we know memory is a precious resource. As a result, managing data is important in memory-intensive applications like interactive analytics engine. But reducing memory comes with a trade-off with performance. To understand this trade-off well, we use uniform replication strategy and run some experiments. In this experiment, we use 20 compute nodes and run 3 different replication factors of 4, 7, and 10. We measure the total memory used on the x-axis and the average query latency on the y-axis. We observe a knee when segments are replicated 7 times. The query performance does not improve as replication grows because over-replication often leads to query hotspots due to data co-location. We have 2 further observations. Finding the right point of the knee depends on the query input rate and the cluster size. As a result, it is very hard to determine it offline intuitively. Lastly, we also ask this question that can we do any better in reducing memory? As it turns out, segment access patterns in these interactive analytics engines are skewed. This is a CDF of segment accesses collected from a trace from production cluster in Yahoo. We observe that a top 1% of the segments are accessed by 43% of the queries, and they are an order of magnitude more than the bottom 40%. These patterns have also been observed in batch processing systems, and typically they have solved this problem by using selective replication. An example system in this space is Scarlet. Scarlet reduces memory by assigning replication based on the number of concurrent accesses a block in a HDFS file sees. We implemented our version of this algorithm and ran the same experiment. We observe a 2.15x reduction in query performance with 1.75x less memory. There are other schemes that look at compressing unpopular data. Note that this is complementary to our work, and in this work we focus on finding better selective replication schemes for this. Concretely, the goal of our system, GetFX, is to occupy this portion of the trade-off space. To break it down even further, we want to minimize memory required with small impact on query latency. We want to minimize make span. And lastly, by minimizing memory, we want to reduce the cost of cluster provisioning. For the rest of the talk, I'll first describe the algorithm that powers GetFX. Next, I'll briefly describe the system design components, and finally, I'll end with evaluation. A typical query in an interactive analytics engine can touch multiple segments. In this example, we have 3 segments and 4 queries. Query Q1 touches segment S1, S2, and S3. We consider a query segment pair as a colored block. A block represents a unit of computation. Its size represents the time it will take to execute the query on the segment. In this example, all blocks are of uniform size, or you can consider them to be of unit query time. The color represents the segment that you're trying to execute. In this example, blue blocks access segment S1, orange blocks access segment S2, and so on. The compute nodes here are the bins. To minimize make span, this problem reduces to a load balanced allocation of these blocks to these bins. Note that we create a replica of a segment when you place 2 blocks of the same color to 2 different bins. So the goal of our problem is to provide a load balanced assignment with the least amount of replication. This is an arbitrary mapping. Note that each bin here has 2 blocks. So this is a load balanced allocation. The number of replicas that each node has, for CN1, this is 2 because there is 1 block of orange color and the other with blue. For CN2, this is 1 because you have both the blocks of color yellow. So the total number of replicas required in this mapping is 7. The solution which minimizes the number of replicas is this one, and here the total number of replicas is 5. To make the problem tractable, we make some simplifying assumptions. We relax all of these assumptions while designing the system. We expect that blocks are of uniform size. We solve for the static version of the problem first, where the balls and the bins are known up front. And finally, we assume the bins are of uniform capacity. Next, we will describe our algorithm. We use a different example for this. The table here lists the segments in the system, and the number represents the popularity, which is the number of queries accessing it. We have 3 compute nodes. A balanced allocation means that each bin will have a capacity of 4. Note that this ensures we minimize make span. We assign this capacity to each bin. Next, we create a priority queue with the segments depending on the descending order of popularity. The algorithm runs in iterations. In each iteration, it picks the most popular segment and assigns it to the compute node based on some predefined policy. If the node does not have sufficient capacity, it returns the rest of the queries to the queue. For compute node selection, we use bin packing heuristics. In our running example, we'll use first fit. We'll pick the lowest ID compute node that is not yet full. So let's return to our example. In this, As we see, segment S1 gets picked first, but it has 6 queries to fit, but compute node 1 has just 4, so it just fits 4 and returns 2 back to the queue. Note that its position changes in the priority queue. The next highest block is S2, and it can fit in CN2. And we continue doing this till the queue is empty. In the next run, we pick S1 again, fit one of the queries, and return the other one back to the queue. And lastly, we fit segment S3 and the remaining balls from S1 and S2. The total number of replicas in this assignment is 6. If you notice keenly that this is not an optimal assignment, as you can get optimal by swapping the blue block in CN2 with the green block in CN3. The final assignment looks like this. It can be shown that among all the load balance allocation, best fit will find the one that minimizes the replication. We refer the audience to the paper for the formal proof. While designing GetFX, we relaxed the assumptions of the last section. We'll talk about it next. The segment replication algorithm is run inside a coordinator node, which is tasked with running and enforcing data management policies. It executes the algorithms in periodic rounds. We implemented an access logger in the compute node, which tracks popularity and sends this to the coordinator. The coordinator then runs the algorithm to find the segment placement plan. While the new placement plan is being generated, queries are still being executed using the old placement plan. That is, we never stop queries from being executed. We run the algorithm so different executions run in small intervals. We chose a small interval to track popularity changes early. As a result, we can handle increased query load to popular segments smoothly. Lastly, the access logger tracks total access time instead of the number of queries. In the earlier section, we assumed that all blocks are of uniform size. But in practice, queries may have different execution profile based on semantics, filter parameters, etc. As a result, the number of queries is not an accurate representation of popularity. Based on the generated segment placement plan, the coordinator instructs the compute node to load or remove segments for the next round. To load a new segment, the compute node fetches the segment from the deep storage. To keep memory utilization high, GetFX aggressively removes unpopular segments. All but one segment can be potentially removed. We don't remove one replica to avoid a network fetch on access. The coordinator can ask the compute node to remove even this replica under resource constraint. For freshly minted segments which have not received queries yet, GetFX bootstrap loads the segments to the compute node. This is done to avoid segment loads on the fast path. We relax our last assumption about the homogeneous compute nodes here. Production clusters are typically tiered with hot, warm, and cold data. Hot data is stored in nodes with memory large enough to fit all the data size. Warm data is stored in nodes with memory large enough to store 30 to 40% of the data size, while the rest is stored in SSDs, and so on. Additionally, you can expect unexpected slowdowns due to stragglers. To handle such heterogeneity, GetFX assigns unequal capacities to the bins based on how much percentage of the query load it handled in the last rounds. Additionally, we also match popular segments to powerful nodes. This is called auto-tiering, and it represents a better alternative to manual tiering done today by sysadmins. There are several other components in our design, and we refer the audience to the paper for more details. Now, we evaluate GetFX and see how it performs with the goals we set out for it. First, let's return to our trade-off plot and see how GetFX performs now. GetFX actually reduces memory use compared to Scarlet by 50%, with 5% additional, 5% more average query latency. GetFX actually performs well at the tail. We have the plot in the paper. Next, we want to quantify how the memory saving scales with increase in query load. We fix the number of compute nodes to 20. We vary the query load by adding more clients plotted on the x-axis. On the y-axis, we plot the memory used by Scarlet divided by GetFX. Note that it is a ratio and higher is better. We observe a 1.45 to 2.15x reduction in total memory for GetFX, and it increases as the number of clients grow. Scarlet alleviates query hotspots by creating more replicas of popular segments, while GetFX carefully places and replicates popular segments, thereby keeping the memory requirement low. Finally, we do some back-of-the-envelope calculations to estimate cost savings. We calculate memory costs as the product of working set data size, replication factor, and the cost of memory. For the first and the last parameters, we use data that is publicly available. For the replication factor, we use numbers that we observed from our evaluation. We know EC2 couples memory and processing code costs, but for the purposes of the back-of-the-envelope calculation, we talk about only memory here. Compared to Scarlet, we estimate a cost savings of $10 million annually. In this last plot, we measured how good our auto-tiering improvements are. We ran our experiment on a heterogeneous cluster with 3 16-core, 6 8-core, and 6 4-core tier nodes. We represent them on the x-axis. On the y-axis, we plot rounds of algorithm execution. We classify each compute node as high, moderate, and low based on the query processing volume it sees. Each division is color-coded. For vanilla GetFX, we observe a lot of hot tier nodes getting moderate and low query volume. This is because they do not have the popular segments assigned to them. With our auto-tiering optimizations, we observe a much better tiering. To summarize, today we talked about the data management problem in interactive analytics engine. It is a very important problem. We showed an algorithm that can provably reduce the memory requirements under some simplifying assumptions. We built our system GetFX, which relaxes these assumptions. Through multiple evaluations, we show that GetFX can reduce memory in practice with little impact on performance. Additionally, our auto-tiering improvements can help a sysadmin do a much better job of placing data to powerful nodes. That's it, and I'm ready to take questions. Thank you.
Okay, let's take some questions. So let me start by asking you two questions. So the first one is, so you have this tuning parameter where you decide how often you want to replan. So can you say a little bit more about the trade-off here and how to set that parameter?
Yeah, so the question is, how do we decide on the tuning parameter? So in general, what we have observed is when we use a very large parameter, then we are not reacting to the query popularity changes that soon, segment popularity changes. And we don't want to run it too fast as well because of the overheads of having to change the segment placement. So in our experiment, we found 5 seconds to be a good ballpark.
Okay.
Yeah.
Okay. And so the other thing that I was wondering, so you didn't say anything about fault tolerance. So can you just say a bit more about how to be fault tolerant with the scheme?
Okay, so the question is about how do we ensure fault tolerance. So in general, Druid, this base system on which we built our system, ensures that all the compute nodes and the coordinator and other nodes kind of don't have a lot of state. So that way, when things fail, you can kind of come up with a new cluster. So in our getafix system, we do not add any state overheads. All the popularity measurements are actually saved to a MySQL instance. And in case if the compute node has to fail, then we can, and a new compute node comes up, it can read the popularity directly from the MySQL. So yeah.
Okay. So last chance to ask any questions. Okay, so let's thank the speaker again. So the next talk is going to be given by Aravinda Prasad, who's a PhD student at the Indian Institute of Science in Bangalore, and he's going to talk about how to make the read copy update synchronization primitive more efficient.
What's the shortcut? Thank you, Peter, for the introduction. I am Aravinda Prasad from Indian Institute of Science. So I'll be talking about a frugal approach to reduce RCU grace period overhead. So let me start with a brief introduction to read copy update. So RCU is a highly scalable synchronization technique where readers do not explicitly synchronize with the writers. Because readers do not explicitly synchronize with the writers, they are highly scalable and they're exceedingly lightweight. So for example, if you look into the non-preemptible kernels, the read-side critical sections are just no op. So they don't change the state of the machine in the read-side critical section. So it is the responsibility of the writers to ensure consistent view of the data structures to the readers. So I always think that RCU is better explained with the help of an example. So let's consider linked list delete operation as an example. So here is the linked list where the writer wants to delete this particular object B. And suppose we have a couple of readers who are actively accessing this object B. As I said, readers and writers do not explicitly synchronize with each other. The writers initially come and remove this object from the linked list. But because there are a couple of active readers who are still accessing this particular object B, the memory associated with this object B cannot be reclaimed until all these readers are done. So what the writers will do is writers will wait, or the writer will wait for these readers to complete before they reclaim. And this wait time is usually referred to as grace periods. So it will wait for a grace period. Once the grace period is complete, it's guaranteed that there are no more readers accessing or actively accessing this particular object B, and the object B can be reclaimed. So it's interesting to see how these grace periods are computed in the Linux kernel. So to compute the grace period, RCU enforces two restrictions on the readers. The first restriction is that the readers are not allowed to access objects outside of the read-side critical section, and it's also applicable in other kind of logs or other kind of synchronization techniques. And the second restriction is that the readers are not allowed to block, sleep, or yield when they are executing within a read-side critical section. So the same rules we have for the task holding spin locks. So with this, the RCU defines something called a quiescent state. A quiescent state is a state where the read-side critical section is not active. So for example, context switch is a quiescent state, because if you are context switching on a non-preemptible kernel, that means we are yielding the CPU. And yielding a CPU is not allowed inside a read-side critical section. We are guaranteed that that CPU is no more running any active read-side critical section. Similarly, transition to user space and transition to idle are also a quiescent state, because we are reading the CPU to user space, and in the idle transition, the CPU is about to sleep. So with this, we know that
a quiescent state on a CPU implies that all the read-set critical sections on that CPU are all done. So the grace period ends once we see a quiescent state on all the CPUs. So for example, in this case, this particular object has been removed from the linked list, and we wait for a context switch on all the CPUs, because when this object was removed, let's see that there was an active reader on CPU 2, which was accessing this particular object. But once we see a context switch, we are sure that the reader is done. So once we see a context switch on all the CPUs, we are guaranteed that there are no more readers accessing this object, and the memory associated with this object can be reclaimed. So with this background, let me start with the motivation for our talk. So the main motivation is that we find that high-performance computing environment and idle environments differ significantly from enterprise environments. So for the enterprise environments, which constitute of mix of compute I/O and network operations, the kernel activity is intensive, and there are a lot of update operations going on. So there will be thousands of update operations going on, and in some cases, it can go up to millions. So this generates a lot of deferred objects. There will be a lot of memory awaiting for reclamation. So in enterprise environments, timely reclamation of the memory is very important. So, but that's not the case in HPC environments, because it's compute intensive, there is limited activity in the kernel, and it generates very less number of deferred objects. So the amount of memory waiting for reclamation is very less. So that is, it's really not necessary to reclaim the deferred objects immediately. And in the ideal case, even it's very less. So we have 1 or 2 objects waiting for reclamation. There is no need to reclaim the memory immediately, because there is no need to allocate that memory or reuse that memory. So the default or the existing grace period computation in the Linux kernel is to compute the grace period as quickly as possible. So what we propose for HPC and idle system is the frugal grace period, where we want to reduce the grace period overhead. So let's look into a couple of RCU overhead. And in the Linux kernel, the grace periods are implemented as a state machine, and it's implemented as a separate kernel thread. So what it means is, to maintain the grace period state, you need to burn some CPU cycles. So you're burning some CPU cycles to compute the grace period. And the overhead of each grace period depends on the number of CPUs in the system. Because as I said, to detect a quiescent state, you have to check all the CPUs. If you have more CPUs, your overhead for grace period computation increases. And new grace periods are started very frequently on the systems, because there are updates going on. So there will be new grace periods started. And the other important overhead is the quiescent state reporting overhead. As I mentioned, every time a CPU context switches, the scheduler will inform RCU that this CPU underwent a quiescent state. So this will add latency to context switching. And this kind of overhead also is incurred when the CPU transitions to user space and CPU transitions to idle state. And interestingly, the CPU still reports a quiescent state even when the grace period is not active. So this will have some impact in HPC and idle environments. The impact is the grace period computation thread can preempt the application threads in HPC, and it can pollute the cache lines, but because it's accessing the tree which consists of per CPU data. And the last one is, when the system is idle, where there is no activity, there is some context switch and interrupts coming in, and the overhead because of this accounts to around 8% of the CPU time. So quiescent state reporting itself will account for around 8% of the CPU time when the entire system is idle. So we have a couple of observations which I have done. So for enterprise workloads, we have seen that the amount of memory waiting for reclamation varies from several MBs to few GBs. And in HPC, it's only few MBs, and when the system is idle, sometimes it's few KBs or sometimes it's few bytes. So, but the grace period overhead is constant because it depends on the number of CPUs. It remains almost around 50 microseconds for all these environments. So if you do the cost comparison and taking the idle system as an example, so in idle system, we have observed that in most of the cases, only one update operation is available in a grace period. So that means we are spending around 50 microseconds to determine the safe time to reclaim a deferred object. So assume we have an object of 32 bytes, and then you spend 50 microseconds to determine whether that object is eligible for reuse or not. But the cost of allocating a new object itself is around 120 to 200 nanoseconds. So what we feel is it's really not economical to burn so much CPU cycles to determine whether a particular object, which is of just 32 bytes or maybe 512 bytes, is reusable or not. Hence, we propose frugal grace periods, an economical grace period computation. And our main design goal is to reduce the overhead of grace period computation, and we do it with two different techniques. So one is to reduce the number of grace periods, and the second one is to reduce the time taken or the CPU cycles consumed to compute each individual grace period. So in the first one, we propose two techniques. One is heuristic-based and the hint-based. And for the second one, we propose two optimizations for the quiescent state reporting and quiescent state forcing. So let's look into this one by one. So in the heuristic-based technique, it's a very straightforward technique where we say that collect garbage only when there is enough garbage. So we don't start a grace period. We wait for the number of deferred objects to accumulate before we start a grace period. So this delays the computation of the grace period, but that's fine in HPC and idle environments. In the heuristic-based approach, we define a systematic way to determine when the grace period is started. To do this, we let the memory allocator hint RCU on when the grace period is required. So we integrate RCU and the memory allocator, and the memory allocator will keep track of the objects, free objects in its pool. And if it's running low of the number of objects in its pool, it will hint RCU that the grace period is required. So then the RCU will start the grace period and the memory can be reclaimed. So, but this technique requires integrating RCU and the memory allocator. So for the quiescent state reporting, the main design motivation is that for HPC and idle environments, the CPU spends most of its time in user space or in idle state. And if we poll a CPU, it's very likely that we'll find that CPU in user space or in idle state. And we already know that a CPU in user space or in idle state is a quiescent state. So that's why a read set critical section cannot be active in this state. So we exploit this information to optimize our quiescent state reporting. So we replace the existing notify-based quiescent state reporting, where the scheduler reports to RCU whenever there is a context switch or whenever it transitions to user space or transitions to idle state, with our poll-based approach. What we do here is the RCU polls the state of the CPU and finds whether it's in user space or in idle state. So this polling is performed only when the grace period is in progress. So if there is no grace period in progress, then we don't do any polling. So, and the other optimization is quiescent state forcing. So if the RCU figures out that the grace period is getting extended for a long time, it starts sending IPIs, inter-processor interrupts, to all the CPUs to ensure a context switch on the target CPU. So, but this is disruptive because it will enforce a context switch on the other CPU. It will preempt the application threads. So what we do is we still send IPIs, but we don't aggressively send IPIs. We just delay sending the IPIs. This will delay the completion of a grace period, but still fine for HPC and idle environments because we don't have a lot of memory waiting for reclamation. So with these optimizations, let's see the evaluation for the idle environments first. So this chart provides the percentage of CPU cycles consumed by tasks when the system is idle. And you can see that the RCU grace period thread, kernel thread, is consuming around 9.6% of the total CPU time when the entire system is idle. So with our optimization, which we use hint-based technique, where we wait for 100 deferred objects to accumulate before we start a grace period, this has reduced to 0.06%. And if we increase the weight, it will further reduce to 0.04%. But so we have reduced the amount of CPU time consumed by the RCU grace period. And if you look into the power consumption, so measure the CPU power consumption, and then we chart it in a histogram with the number of instances in the y-axis. So we can see in the CPU spent around 1,800 instances in 55 watt. With our optimization, it has doubled. So most of the time, the CPU spends in lower watts, so with our optimization. And a couple of statistics related to the RCU grace period. So this is the CPU cycles consumed by the grace period thread. It has reduced drastically And this is the overhead of quiescent state reporting when the system is idle. So it has reduced from 8% to less than 1%. And if you see the number of updates handled per grace period, it was around 1.3 on an average. So it's around 400 to 500 with our enhancement. And with all this, it's also important that we do not have much impact on the memory allocator. Because we are delaying the completion of a grace period, we should also ensure that it will not have, it won't impact the memory allocator. So if you look at the memory allocator statistics, because of the delay in the reclamation of the deferred object, there's a slight increase in the memory footprint, or the amount of memory requested by the slub memory allocator in the Linux kernel. It's around 50 bytes of additional memory requested. So we feel that's fine, provided these systems are equipped with GBs of memory. And moving on to evaluation in HPC environments, we evaluated the NAS parallel benchmarks, and we see similar results. So the grace period rate has decreased, and the amount of time the grace period is consuming has decreased for all the cases, and the memory is also almost the same. And sometimes it has improved, and sometimes it's a bit more. It's around 4 to 5 GB more, and I think it's still fine for systems with GBs of memory. And we see a lot of improvement in the throughput for a couple of these, and around 5% improvement for a couple of these kernels for NAS parallel benchmarks. To summarize, grace periods are the critical component of the RCU, and it determines the safe time to reclaim the deferred objects. And the existing or the default grace period computation employed in the Linux kernel will work fine only for the enterprise workloads. What we propose is frugal grace periods that is optimized for HPC and idle environments. The source code is available in GitHub, so for both of the hint-based and heuristic-based techniques. So with that, I would like to thank you and open up for questions.
Thank you. Questions? So one thing that I was wondering is that, so what are particular HPC workloads for which your approach does not offer much benefit? So how do I know that I have a workload where this won't buy me much?
So one thing you can do is you can profile this kernel and see how much deferred objects the workload is generating. And if you see that the number of deferred objects which the workload is generating is very less, then this is the one which you can opt for. But if it's generating a lot of deferred objects very frequently, then this may not work.
Right, right.
Is there any experimental evidence of this scheme not working for enterprise systems? I understand that you talked about memory reclamation cannot be delayed there, but I'm just curious, like if you were to have a dynamic scheme which would exist in enterprise systems and kick in only when the right case arises. Have you tried that experimentally?
Yes, we have evaluated on the enterprise workloads, and the results are available in the paper. So there is not much impact on this throughput. There is only 2% impact on the overall throughput. So we evaluated on Postmark, MKHD, and Apache web servers. And there is no impact because the limit of 100 objects after which we start a grace period is very less. So in enterprise workloads, there are around thousands of objects generated during a grace period. So that will delay the grace period only by a couple of microseconds. And that's not impacting the actual throughput of the enterprise workloads. And the evaluation is presented in the paper. So we do have that in the paper.
So can I also ask, so if you wanted to get this upstreamed in the Linux kernel, so how extensive were the changes?
So hint-based is a small change. Heuristic-based is a small change. So we just delay the starting of a grace period before, and then just stop the grace period computation. It's a small change. But the other heuristic-based is a bit complex because we are integrating the slub allocator and the RCU allocator.
Okay, so if there are no, there's one more question there.
Thank you. Could you briefly comment on how comment on how this compares to the parallel sections that were presented last year? So RCU based on the timestamp counters.
So I'm sorry, I didn't quite get your question. Can you be?
So RCU, but using timestamp counters to detect grace periods.
Okay, so I have not explored that. So RCU using time-based counters. So I think those are basically used in the user space RCU. So but kernel space RCU is different because it relies on the context switch. So that's the crucial information on when the read-set critical sections are complete. So, but in user space, the readers will explicitly inform that it's not inside any read-set critical sections. So those optimizations are different in user space, I feel.
Okay, so let's thank the speaker again. So the fourth presentation will be given by Asaf Eisenman, who is a PhD student at Stanford University, and he'll be talking about the work that he's done with Facebook on reducing memory foot shuffle in data analytics.
Okay, thank you, Peter, for the introduction. Thank you all for staying here for the last talk of the conference. Today I'll be talking about how shuffle could become the scaling bottleneck for big data systems and how our solution Riffle solve this problem and make the system scales to process petabytes of data. As we all know, big data analytics are widely used in big companies such as Facebook and Google for processing large-scale SQL queries, custom batch jobs, and do pre-processing and post-processing for machine learning workload. The data that is getting processed by these systems is growing super fast. For example, the Spark deployment at Facebook is processing tens of petabytes of newly generated data every day. One of the largest jobs takes in more than 100 terabytes of data per day. In addition to the fast-growing data volume, the query processing logic is also getting more and more complicated. Here is an example of a distributed SQL query, where it first reads in the two datasets from two separate tables, performs some transformations, joins the two datasets, repartition the dataset according to a certain field, filter out irrelevant items, and save the results into a separate table. We can see two types of relationships between these operators. One is narrow dependency, in which case the operation on the subsequent partition only relies on the result from one of the partitions in the previous operator's result. And there's also wide dependency, in which case the subsequent operators relies on all the results from the previous operators. So if you submit such kind of a logical query into an engine like Spark, you will get a DAG execution plan like this. So in this graph, each big and shadow box here is the state of the dataset during the transformation. And each small solid box is a task performing the computation on a certain partition of that dataset. So if you only have narrow dependency, then Spark is going to use memoization technique to pipeline the execution of multiple operators on a single partition by caching that partition in memory. So if you have wide dependencies, then each task in the subsequent stage will have to retrieve a corresponding block from all the partitions in the previous stages. So that means that there is an all-to-all communication pattern going on between the two stages, and we call this communication pattern a shuffle operation. So in fact, the shuffle data has to be kept on disks for two reasons. First is that in production jobs, the data that is getting processed during the shuffle is more than 10 times larger than the available memory space. So it's not possible to cache the data entirely in memory. The second reason is that large-scale data processing requires strong fault tolerance. So let's assume that if you only cache the data inside memory, then even a single task failure in the subsequent stage will cause the recomputation of all the tasks in the previous stage. So that will make the failure recovery overhead too huge. Recent academic research work raises an interesting topic to accelerate big data system by simply slicing the dataset into smaller or tiny tasks. This so-called tiny task execution plan surely has several benefits. For example, it gives you better level of parallelism and better load balancing, and you can also like mitigate the structural overhead by just doing speculative execution. However, if you look at the engineering experience, the engineers often argue against this tiny task execution plan. Here we cite from an article published in an engineering blog, saying that we found there is a significant performance degradation when the number of tasks is too high. So what is the reason behind this mismatch between the engineering experience and the research work? We believe the reasons is actually twofold. One is that if you look at the research work, when they experiment their system, they often run like medium to small scale data set, and they often over-provision the resource so that you can cache the entire data set in memory. But as we said before, this is not the case for production jobs where you have typically 10 times larger data than the available memory space. The second reason is that a lot of benchmarks only provide you single-stage jobs that are embarrassingly parallelizable. But with a complicated query logic in production jobs, they are typically multi-stage jobs with at least one shuffle operation involved. For example, at Facebook, we know that more than 50% of the Spark jobs are multi-stage jobs with at least one shuffle operation. So running a large number of small tasks in multi-stage job can incur your performance, can incur huge overhead in your performance. So let me explain what is the reason behind this. So from this graph, we can see that when the size of the data grows, the number of tasks in both the map and reduce stage are proportionally growing. And that makes your shuffle operation, which is all-to-all communication pattern between the map and reduce, actually growing quadratically. To prove that is actually the case, here in this graph, we run fixed-sized tasks, and we let the job scale by increasing the number of tasks in both the map and reduce stage. In the orange line, we can see that the number of shuffle I/O requests is actually growing quadratically. And because the disk seek time during this operation is actually dominating the shuffle time, so in the green line, we also see that the shuffle time is increasing quadratically. And if you do the math here, because your data is only growing linearly, but your number of shuffle operation grows quadratically, so the average size of each shuffle request is actually decreasing. So what that means is that as the data grows, there are more and more large amount of there's a large amount of fragmented small random I/O that is exactly the adversarial workload for your hard drives. That can make the shuffle performance really bad. So one strawman solution to mitigate this problem is that when your data grows, you don't let the number of tasks grow. Instead, you fix the number of tasks and just let the individual task partition grows. The problem with this solution is that when the task is exceeding the executor's memory space, then you will incur an additional disk spills problem. So here is what's going to happen if your task is twice as large as the memory space of an executor. So when you launch the task, it will first read in the first half of the partition, process it, and save the result to disks. And then you will read in the second half of the dataset of that partition and perform the transformations, and then write the result to disks. And eventually, you're going to have to use external sort to merge these two intermediate files into one large shuffle file. And the same thing has to happen for all the other tasks as well. So if you run a as we can see from here, if you run a small number of large tasks, that will give you less shuffle overhead, but inevitably that will incur a huge disk spills overhead. So there is an inherent trade-off between the shuffle I/O and the spill I/O. So in this case, let's run a fixed size job, and we vary the number of map tasks for this job on the x-axis. And the more towards the left, that means that we're running a smaller number of tasks, but each task is getting larger. So as we expected, the shuffle overhead is decreasing towards the left. But at the same time, you will incur larger spill overhead. So what the engineers will have to do is to tune the number of tasks in each stage to find this sweet spot that incur the least shuffle plus spill I/O overhead. And in this case, that means that we want to run 1,000 tasks in the map stage. Well, this approach only works if you run this tedious experimentation with different configurations of this job, and this is certainly not a attainable solution for thousands of jobs at Facebook. And another reason is that running a large task or running these bulky tasks is generally a very bad idea because it will incur a significant straggler problem and imbalanced workload and garbage collection overhead. To summarize what we've just talked about, we wanted to run small tasks for better parallelism, but unfortunately that will give us a large amount of fragmented I/O problem. So we want to have fewer and sequential I/O requests during the shuffle stage, but that will create bulky tasks, which is also very bad for your execution. So our question is, how do we design a shuffle system so that we can benefit from both the small tasks and the fewer and the sequential shuffle I/O? Our solution is Riffle, which is an optimized shuffle service for big data analytics. So here is the general architecture for a big data system. You will have a driver that assigns tasks to a number of worker machines. Each worker machine will run these tasks inside some executors and write the output of the tasks to a distributed file system. These workers will also report back the task execution status to the driver. So in addition to this component, Riffle will add an external shuffle service on each worker machine, and it will also add a component inside the driver to schedule these merge behaviors. So what the merge scheduler will do is that it will send out the merge request, and when the merge instances on these individual workers receive those requests, it will merge the intermediate fragmented shuffle files into larger chunk files, and then it will return back to the scheduler reporting the status of the merge request. So here, let's zoom in to what will happen if you send a merge request to the worker. Assume that in this, on this worker node, there are 5 map tasks finished. And each map task is going to generate this kind of intermediate shuffle file, and the keys and values in this shuffle file are partitioned according to the reducer's partitioning function. When we receive a merge request, then this merger is going to, let's assume that the merge request wants to combine every 3 shuffle files into one large chunk file. So what the worker-side merger will do is that it will combine the small shuffle files into larger ones, and it will keep the original file layout. So you're merging this chunk by chunk. So note that the merged file is also partitioned according to the reducer's partitioning function. So right now, if you launch the reducers, instead of reading from a large amount of fragmented small shuffle files, it will just send much fewer shuffle read requests from these merged shuffle files. So that essentially gives you a huge win in the number of shuffle I/O requests during the operation. So to show the benefit of this efficient merging in Riffle, we first look at the synthetic workload that processes 3 terabytes of data. So note that in this synthetic workload, the map stage is only doing the file generation, and the reduce stage is only doing the shuffle operation. So there's no heavy computation involved in this job, so that we want to isolate the shuffle behavior. So on the x-axis, we show the results of unmodified Spark with no merge, and also Riffle with different merge policies, such as 5-way, 10-way, 20-way, and 40-way merges. So as we can see from this from this orange line, as we are merging more aggressively, the number of read requests during the shuffle operation is decreasing very fast. Effectively, we can reduce the number of shuffle requests by more than 10x. So when that gets translated to the end-to-end shuffle stage computation time, then here's the result. So from the orange line, we can see that the reduce stage is shortened a lot, and overall the job is completed 35% faster. Unfortunately, there is still a big overhead in the map stage. So here, the map stage actually includes all the map operations and the merge operations, which are both blocking the starting time of the reduce stage. So how do we deal with that? So our observation is that the map stage delay is mainly due to the straggler problem. So there will always be some map tasks that finish much later than the majority of the rest, so that the final several merge operations will have to wait for these map tasks to finish before it can start the merge operation. And only by finishing your merge operation, you can start the reduce stage. So So we introduced a mechanism called best effort merge, which we allow users to set a percentage threshold to the refill scheduler. So that means that when the refill scheduler receives that amount of returned merge request, then it's not going to wait for more merge requests to return, but it will immediately start the reduce stage. But don't worry, the merge scheduler is going to make sure that all the reducers read from the corrected blocks, either from the merged format or the unmerged format with no omission and no repetition. So here is the result if you set the best effort merge threshold to be 95%. We can see that on the graph on the right shows that the reduced stage time is almost not affected, but there is a huge saving in the map stage time. So in this case, the overall job completion time is 53% faster compared to the vanilla Spark. So that means that refill can effectively use only half of the resources to finish this job. So there's a couple additional enhancements, including how we handle the merge operation failures, how we manage the memories, and how we balance the merge request workload. So I refer you to see our paper for details. So to run the experiments in the production workload, we picked 4 representative jobs at Facebook. The first one is a relatively small-scale job that processes hundreds of gigabytes of data. The second and third one are medium-scale jobs, and the last one is a large-scale job that takes in more than 260 terabytes of data. So note that the fourth job is actually processing a key data set, whose result is going to be used by a lot of downstream jobs. So accelerating the runtime of this job will not only benefit itself, but also reduce the landing time for a lot of other jobs. So we first look at the I/O efficiency. This figure here shows different jobs on the x-axis and the total shuffle I/O request on the y-axis. The colors here show different merge policies to get the merge block size of 512 kilobyte, 1 megabyte, 2 megabytes, and 4 megabytes. So we can see that the refill reduces the number of shuffle I/O requests by 5 to 10x for medium to large scale jobs with for example, 2 megabyte merge policy. To look at how this converts to the end-to-end job completion time, here is the result. So the y-axis here in this graph shows the total task execution time in terms of CPU days. So we can see that on each bar, the top part without the hatches is a map stage time, and the bottom part of the bar with the hatches is a reduced stage time. So with best effort merge enabled, we can see the map stage time is almost not affected, but there is a huge saving in the reduced stage time. So overall, we can see that the refill could effectively reduce the job completion time by 20 to 40% for medium to large scale jobs. To summarize, refill provides an optimized shuffle service for big data analytics systems. And refill specifically targets for running large-scale, multi-stage jobs. It solves the fragmented shuffle I/O problem by efficiently merging the fragmented intermediate shuffle files to larger block files. And the system is now deployed to Facebook, processing petabytes of data. With that, I'd like to conclude my talk, and thanks for your attention. I'd like to take any questions.
Hi there, thanks. Great talk. Dushint Narayan, Microsoft Research. I was just wondering, in your experiments, if you ran local combiners on the machines running the map tasks, and how much difference that made to the amount of shuffle data. Because depending on the kind of workload, you could potentially make the problem you're solving go away by just reducing the amount of data to be shuffled. So I was curious about, in your real workloads, what you found.
So if I understand correctly, the question is, why is our merge service reducing the data that you need, the volume of data you need to shuffle?
No. Did you try using local combiners to reduce the amount of shuffle data? And does your method still show benefit when you do that?
Good. So the question is that there is a combiner that is available in Spark that can combine the local files and into larger files. Yeah. So in terms of like mechanism, conceptually it's similar to Riffle, but there are several key differences. So first, Riffle is operating on the files on each worker instead of each executor. So the combiners can handle the intermediate files generated by the same executor, but not from different executors, even though they are on the same machines. The second is that during the merge, we're doing, if you look at the paper, we're designing the merge service to be very efficient, working on serialized data without actually interpreting the data. So the combiner, the way it works is that you will deserialize the data, convert that to in-memory representation that is the object, then you sort them, then you serialize the data again. But Riffle, our design is that we are directly working on the serialized data, so we incur the minimum overhead compared to the combiner solution. Yeah.
So any other questions?
Does it work? Okay. Basically, the Untitled algorithm works because every task has mixed set of keys. But sometimes we can have already sorted data, or when it's ideally partitioned, when we have a hash partitioner. Or my question is, how is it realistic that already data sets can be sorted or partitioned in a nice way, not like what you have on the left slide? Basically, it can be already merged somehow. And we don't need to merge data because it was pre-merged for us when we read it from the disk. How's it like? Is it a realistic assumption in the real workloads? And basically, what if it turned out that your data is already pre-merged and basically you don't change your keys? What your algorithm is going to do with this?
All right. So our understanding is that we only target the jobs with significant shuffle overhead. So if the data is already pre-partitioned and the task in the reduce stage would only like read from specific partitions in the map stage because they are pre-sorted, then the shuffle overhead for those jobs are just not that significant. So there's not a huge saving if you run Riffle on those shuffle workload. But the fact is that when we look at the production jobs at Facebook, a lot of these jobs will not be that ideal, right? So when we apply Riffle on those tasks, we see a huge benefit. Yeah. Okay, thanks.
Okay, so this is your opportunity to ask the last question at Eurosys 2018. That is a great honor. You can put it on your CV. Anybody? Otherwise, I'm going to do it. Okay, so one thing that I was wondering is that, well, so you argue that the problem comes from the fact that with those fine-grained I/O requests that you get in the shuffle phase, you experience performance problems. But won't this issue go away, right? I mean, once we move to effectively different storage technologies that don't have that problem, I mean, are there sort of any lessons from your work that will then still be applicable?
Yeah, great question. So the question is that if the underlying storage system changes, then will Riffle still benefit for your storage system? So we've certainly considered SSD. So there are certainly a lot of SSDs deployed in data centers, but those SSDs are more. We found like currently. The major reason is that it's for the cost effectiveness. So using SSDs for example, like storing social graphs and Facebook's photo caching is very effective because you store it once, but you read it a lot of times. But for the intermediate shuffle data, you only read it once and read it once. So there's not much benefit from it. And also, like because of the large volume of data churning, then you will soon run out your SSD cycles. And nevertheless, so the goal of Riffle is that it will provide you this sequential I/O behavior, even though you are just using traditional hard drives. So we will provide you this benefit so that you won't have to worry about the fragmented I/O problem with during the shuffle and when your job scales. And I think that benefit is going to carry over even though you work on more advanced storage technologies, because right now you can get rid of a lot of write requests, and that is going to in general benefit your storage system.
Okay, so let's thank the speaker again. So this concludes the session, and I will now pass the mic to Rui, who will close the conference. Rui, where are you?
Okay, so this is it. Thank you very much for coming to Porto. I'm sure you enjoyed the event. That's what I've been told by every single one that I talked to. So apparently the temperature will go down today and rain will come back. So this was exactly the time slot for you to enjoy the good weather in Porto. So before ending, I would like to ask my team to come to stage. All of you, of course. So, as you can see, I didn't do anything. So, it's a big team. I'll try to name them all. Rafaela, Stephanie, Vitor, George, Paula, Fabio, Adrianson, Rogério, Ricardo, Nuno, Chico, Francisco, Nuno, Francisco Neves too, Leandro, João, Rui, Catarina, Lídia, Daniel, Francisco and Diogo. Okay, so all of them were at your service. A big applause for them.
Basically, didn't check the